Hi friend, welcome all to my educational channel Math A to Z. This is the second and also the last class of Wronskian. At first we state and prove an important theorem of Wronskian as the Wronskian of two solutions of the equation a0x into d2y by dx2 plus a1x into dy dx plus a2y equal to 0, where a0x not equal to 0 and x belongs to AB, open interval AB, is either identically 0, Wronskian is either identically 0 or never 0 on AB. Okay, that is the Wronskian is either identically 0 on AB or never 0 on AB. Here the equation is given by this, where a0x not equal to 0 and x belongs to AB, and this is named as 1. From this we can write y double dash equal to minus a1 by a0 into y dash minus a2 by a0 into y. Since let y1 and y2 are two solutions of 1, then these two solutions must satisfy 2. That is, we get y1 double dash equal to minus a1 by a0 into y1 dash minus a2 by a0 into y. This is 3, and similarly y2 double dash equal to minus a1 by a0 into y2 dash minus a2 by a0 into y. Sorry, this is y1 and y2, and this is 4. Now Wronskian of y1 and y2, that is the Wronskian of two solutions, is Wronskian of y1 y2 or Wronskian of x is equal to determinant y1 y2 y1 dash y2 dash, and this is y1 y2 dash minus y2 y1 dash. This is named as height. Now we differentiate the Wronskian w with respect to x, and from height we get the result w dash. This is obviously equal to y1 y2 double dash minus y2 y1 double dash. Now putting the value of y2 double dash and y1 double dash from 3 and 4, we get the result as this is equal to minus a1 by a0 into y1 y2 double dash minus y2 y1 double dash, y1 dash. We get the result by putting y2 double dash and y1 double dash from 3 and 4, we get this result, and this is obviously minus a1 by a0 into Wronskian. So we at last reach at the position as Wronskian of x and its derivative is equal to minus a1 by a0 into Wronskian of x, and this is 6. Now here two cases may arise. First case, First case, if Wronskian of x not equal to 0 for all x belongs to AB, then we easily say that the Wronskian never 0 on AB, because we assume Wronskian of x not equal to 0 for all x belongs to AB. And if we take Wronskian of x equal to 0 at x equal to x0 belongs to AB, then we get Wronskian of x0 equal to 0, and from the relation 6 we get w dash x0 equal to minus a1 by a0 into w x0, and this is equal to 0, so this is 0. And since Wronskian of x 0 equal to 0 together with Wronskian dash x0 equal to 0, so we must say that Wronskian of x equal to 0 for all x belongs to AB. We know this result from, and this is discussed in previous class of Wronskian. So we say that the Wronskian of x is equal to 0 for all x belongs to AB. That is, the Wronskian is identically 0 on AB. Okay, and this proves the theorem. An important deduction from this theorem we get as from this result 6, we get dw by dx equal to minus a1x by a0x into Wronskian of x, and it can be written as dw by w equal to minus minus a1x by a0x into dx, and by integrating we get log w equal to minus integration a1x by a0x into dx plus log capital A, and this gives Wronskian of x equal to a into e to the power minus integration a1 by a0 into dx. Okay, and this is the value of the Wronskian, where a0, a1 are known coefficient, a0, a1 are known coefficient from the differential equation. Okay, and this is also an important deduction of Wronskian. The second theorem of the class, there exist two linearly independent solutions y1x and y2x of a0x y double dash plus a1x into y dash plus a2x into y equal to 0, where a0x not equal to 0 for all x belongs to AB, then every solution y of x may be written as y of x equal to c1 y1x plus c2 y2x, where x belongs to AB for suitable constant c1 and c2. Okay, here the statement is there must exist two linearly independent solutions of this second order linear ordinary differential equation, and if y1 and y2 are two linearly independent solutions, then any solution of the equation can be written as this, where c1 and c2 are two suitable constants. Before going to prove this theorem, we here prove an important theorem which states that if y1x, y2x be any two solutions of this differential equation, then the linear combination c1 y1x and c2 y2x and the sum of these two, that is the linear combination of y1x and y2x, is also a solution of this equation. Okay, very easy proof. Since y1x and y2x are the solution of this, so we can write a0 y1 double dash plus a1 y1 dash plus a2 into y1 equal to 0. And also for y2 we get the same result as a0 y2 double dash plus a1 y2 dash plus a2 into y2 equal to 0. Now multiplying this relation by c1 and this relation by c2 and adding them, we get a0 into c1 y1 double dash plus c2 y2 double dash plus a1 into c1 y1 dash plus c2 y2 dash plus a2 into c1 y1 plus c2 y2. This is 0, and this relation can be written as a0 into c1 y1 plus c2 y2 whole double dash plus a1 into c1 y1 plus c2 y2 whole dash plus a2 into c1 y1 plus c2 y2 equal to 0. And this relation shows this satisfies the given equation. So this must be a solution of the given equation. Clear? So we get an important result that if y1 and y2 are any two solutions of a linear second order homogeneous differential equation, then the linear combination of these two solutions is also a solution of the same equation. Now go to the proof of the theorem. Here the given equation is a0x y double dash plus a1x y dash a2x plus y a2x into y equal to 0. This is the given equation where a0x not equal to 0 and x belongs to ab. This is named as 1. Let x0 be any point on ab or in ab, and y1x and y2x are any two solution of 1 satisfying y1 x0 equal to 1 and y1 dash x0 equal to 0. This is named as 2, and y2 x0 equal to 0 but y2 dash x0 equal to 1. These two results we assume, where y1 and y2 are two solutions satisfying this relation. Now we first prove the solution y1 and y2 are linearly independent. If not, let y1 and y2 are linearly dependent. And since we take y1 and y2 are linearly dependent, so there must exist two arbitrary constants c1 and c2, not both 0, such that c1 y1x plus c2 y2x is equal to 0 for all x belongs to ab. And differentiating we get c1 y1 dash x plus c2 y2 dash x equal to 0. This is also for all x belongs to ab. Okay, and since x0 belongs to ab, so we must have c1 y1 x0 plus c2 y2 x0 equal to 0 and c1 y1 dash x0 plus c2 y2 dash x0 equal to 0. Using the result 2 and 3, we get, if we put y1 x0 equal to 1 and y2 x0 equal to 0, from this relation we get c1 equal to 0, and putting y1 dash x0 equal to 0 and y2 dash x0 equal to 1, we get the result c2 equal to 0. But we here assume C1 and C2 are not both 0. So there is a contradiction that since we take y1 and y2 are linearly dependent. So here we prove that y1x and y2x must be linearly independent. Right? Now we go to the second part of the theorem. Here we let y of x be any solution of 1 satisfying y of x0 equal to c1 and y dash x0 equal to c2. Right? And these two is named as 2, or this name is not required. Y of x be any solution satisfying these two relations. Okay. Now we take u of x is equal to y of x minus c1 into y1x minus c2 into y2x. Here y of x be a solution of 1. Here we assume. And y1x and y2x are also two solutions of 1. It's a given. So these three, yx, y1x and y2x, these three are the solution of 1, and this is the linear combination of 3 solutions. And we know that the linear combination of the solutions of a second order differential equation is also a solution of this differential equation. So we say that u of x must be a solution of the differential equation 1. Now differentiating this, we get u dash x. This is equal to y dash x minus c1 into y1 dash x minus c2 into y2 dash x. And since x0 belongs to AB, so if we put x0 here, we get u of x0 is equal to y of x0 minus c1 y1 x0 minus c2 y2 x0. Okay. Now using this result, y of x0 equal to c1 and y dash x0 equal to c2. Also we write u dash x0 equal to y dash x0 minus c1 into y1 dash x0 minus c2 into y2 dash x0. In the first case, we take y1 x0 equal to 1, y1 dash x0 equal to 0, and y2 x0 equal to 0 and y2 dash x0 is equal to 1. This result is also required for this case. Okay, so we write here again. Now putting this value y of x0 equal to c1 and this value and this value here, we get this is equal to c1 minus this is also c1 and this is 1 and this is c2 into 0. So we get the result as c1 minus c1. So this is 0. Also, if we put this result and this result in this equation, similarly we get this is also c2 minus c2. This is also 0. Right? So we get u of x0 equal to 0 and u dash x0 equal to 0 for x0 belongs to AB. So we must say that u of x equal to 0 for all x belongs to AB. Right? Now putting u of x equal to 0 here, we get this is 0. We get the relation as y of x equal to c1 y1x plus c2 y2x, and this is the proof of the second case, because y of x be any solution and y1x and y2x are the independent solution of 1. So we say that any solution y of x can be written as the linear combination of two independent solutions, where C1 and C2 are the suitable constant. Here we consider a very easy example to show the uses of Wronskian. The example is so that sin 2x and cos 2x forms a set of, this is set of fundamental solution of y double dash plus 4y dash equal to 0, and hence find the general solution. If we take y1 equal to sin 2x, clearly this sin 2x satisfy this, that is y1 double dash plus 4y1 equal to 0, and similarly if we take y2 equal to cos 2x, then it is also y2 double dash plus 4y2 equal to 0. So these two are the solution, and to prove these two are the fundamental solution, we have to show that these solutions are independent. The fundamental solution means the solutions are independent. So we find out the Wronskian of sin 2x cos 2x. This is sin 2x cos 2x, 2 into cos 2x minus 2 into sin 2x, and this is minus 2, and obviously this is not equal to 0. So y1 and y2 are linearly independent. So we prove that the solutions are fundamental solution, and we already see that in the previous theorem, since y1 and y2 are the fundamental solution or independent solution, so the general solution of this equation can be written as y of x equal to c1 into sin 2x plus c2 into cos 2x. Okay, this is the general solution of the differential equation, and this is the solution of the example. Okay, thank you for watching.